Dr. Pavitra Bharadwaj, Associate Professor in the Computer Science Department of Jesus and Mary College, University of Delhi. So, we were talking about CPU scheduling in the last lecture, and this is in continuation to our discussion in that lecture. We were talking about the round robin scheduling algorithm, in which we had seen that the round robin algorithm, it's implemented in the form of a ready queue, just like in FCFS, but here another dimension or another matrix is added, that is called the time slice. Why is this done? Because round robin scheduling algorithm is most appropriate for time sharing systems. So, every system, every process in the system is going to get one time slice or one time quantum, and if the process is able to if the process is able to finish its CPU burst within the one time quantum, then the process will itself release the CPU voluntarily, right, and then the scheduler can pick up the next process in the ready queue. But if the process requires longer time than the quantum unit, say for example, the process requires 24 milliseconds and the time slice is 10 milliseconds, then what will happen? After the first time slice is expiring, after the quantum is expiring, then the process will be preempted and the CPU will be assigned to the next process in the queue, and the process which was executing, which is still remaining, will be put back into the tail of the ready queue. It will come back to the tail end of the ready queue, right. So, if this is going to happen, like if the CPU burst is longer than the time quantum, then the preemption strategy will work. So, CPU scheduler will keep on selecting the processes and assigning them the CPU only for a fixed volume of time, only for a fixed quantum of time. Now, average waiting time under the round robin algorithm is also quite long. So, if we see in this example, we have 3 processes and the burst time required by each is 24, 3 and 3 milliseconds respectively. Now, if in this case we use a time quantum of 4 milliseconds, so then what will happen? Process 1 in this case will use the CPU for 4 milliseconds, but the requirement of the process is 24 milliseconds. So, after the 4 milliseconds, the CPU will be preempted, the process will be preempted and processor will be assigned to the process P2. Now, P2 requires the CPU only for 3 milliseconds, which is less than the quantum. Quantum is 4 milliseconds. So, before the quantum expires, process P2 finishes and then the CPU is assigned to process P3, which also requires only for 3 milliseconds. After this, after process P2 and P3 have completed, then the CPU will be assigned back to process P1, who is still left with 20 milliseconds of its CPU burst. So, after this, the process P1 will have the complete write. Why no change? Because after this no process is coming. Each process will receive one time quantum and the CPU will be returned to the process for the additional time quantums which are left. Now, what is the waiting time in this? So, the waiting time for process P1 will be 6 milliseconds, because it is initially it gets the CPU, but after that it has to wait for 6 milliseconds to get the CPU. P2 will wait for 4 milliseconds and P3 will have to wait for 7 milliseconds. So, in totality the average waiting time will come out to be 5.66 milliseconds. So, therefore, we say that the average waiting time in the round robin algorithm is quite high. It is for 3 processes, it comes out to be 5.66 milliseconds. Now, besides this waiting time, there are other dimensions also which we have to be conscious about, because round robin scheduling process is allocated the CPU for more than one time quantum in a row, unless it is only one process. If it is only a one process, then of course it will be running solely. But if you have more than one process, then continuously the CPU is to be changing context between processes after every time quantum elapses. So, the process is preempted and it is put back in the ready queue. So, therefore, round robin is preemptive. Now, whenever we have a preemptive process, whenever we have a preemptive algorithm, another overhead is added to the total time, which is known as the context switch time. So, that also is very important. Now, if we understand it this way, that if there are n processes in the ready queue and time quantum is say q, each process will get 1 upon n of the CPU time in chunks of at most they will get q time. So, each process will have to wait for at least n minus 1 into q time units for its next turn. Or otherwise, if we understand it in direct terms, say for example, there are 5 processes and a time quantum of 20 milliseconds is assigned. So, each process will get 20 milliseconds after every 100 millisecond, because no process can get more than the quantum. So, every process will get 20 milliseconds and then it has to wait for another 100 milliseconds to get the CPU back, right. So, therefore, we say that the average waiting time in this is quite high. Now, also the performance of this algorithm will be very highly dependent upon the size of the time quantum. That is, we have to understand that the size of the time quantum, if you keep it extremely large, then your round robin is nothing but it is an FCFS policy. Why? Because the process will not be preempted and it will have the CPU with itself unless it gives it to the next. But if you keep a time quantum of very small, say for example, you keep a time quantum of 1 millisecond, then it will require a large number of context switch. That is, after every 1 millisecond, the CPU will have to switch to the other process. So, this another overhead which is added is this. So, a balance has to be found out between what should be the time quantum. So, we are going to look at this, that what is the ideal or what is the most suited time quantum which can be utilized here. So, if we look at this diagram shows the effect of quantum size on context switches. That is how the quantum size is going to determine the number of context switches. So, if we have a quantum time of say 12 milliseconds, right, and the process requires 10 milliseconds, right. So, in that case the context, there will be no context switch because the process will complete in 10 milliseconds, whereas it is given 12 milliseconds. So, there in that case, when the process time is less and the quantum time is more, there will be 0 context switch. Another could be if your quantum is 6 milliseconds, right. Now, your process requires 10 milliseconds. So, there will be 1 context switch because the process will have the CPU for the first 6 seconds. After that, the CPU will be given to another process and then this process will have to wait. So, if you have it for 6, then there will be 1 context switch. Now, if we look at the extreme end where we have the quantum of 1 millisecond, that is the process will get the CPU only for 1 millisecond at a time. In this case, how many context switches are going to be there? There will be 9 context switches within the given 10 seconds, right. So, therefore, we see that in this case, the context switch overhead is going to be a big burden on the CPU because the process is executing and before it finishes another process like this, there are 9 context switches which are happening here. So, therefore, we want that the time quantum should be large with respect to the context switch time. You cannot have them almost equal, right. So, in most of the studies which have been done, the context switch time is approximately 10% of the time quantum. Then about 10% of the CPU time will be spent in context switching because you are wasting 10% of the CPU time only for lodging and dislodging the processes. So, most modern systems of today, they keep a time quantum ranging from 10 to 100 milliseconds. So what is this? This is the time required for context switch, which will be less than 10 microsecond, right. So what we are seeing is that the context switch time should be a very small fraction of the total time quantum. Otherwise the entire exercise of this scheduling is going to lose its meaning, because the CPU is spending considerable amount of time only in switching between processes. Another very important attribute that we had discussed in earlier lectures was the turnaround time. So turnaround time, we had seen that it is the time which is elapsed between the process entering the system first till the time the output is generated, or till the time it completes, right. Now this also will depend upon the size of the quantum. Why we say so? Because the average turnaround time of a set of processes will not necessarily improve if you increase the time quantum much, right. So average turnaround time can only be improved if the processes finish their next CPU burst in a single time quantum. So the idea is that around 80% of the processes, if they complete within the single time quantum, then the round robin algorithm is a very efficient algorithm. Like if we take the example of 10 time units, there are 3 processes which each needs 10 time units, and the quantum of 1 time unit, the average turnaround time will be 29 milliseconds, right. If you keep a time quantum of 10, in that case it is going to be like this, right. So average turnaround time will drop to 20 if you keep the turnaround time to, if you keep the quantum time to 10, right. So because context switch is added in the average turnaround time, which increases more for a smaller time quantum, since more context switches are required. So again that point becomes more clear, that not just waiting time but also turnaround time has to be optimized, keeping the size of the time quantum in mind. So now time quantum should be large with compared to the context switch time, but it should not be too large also, so that your round robin starts behaving like the FCFS, right. So therefore it is large enough, but it is not too large also. Now what is the rule of thumb? The rule of thumb is that it should be 80% of the CPU burst should be shorter than the time quantum. In that case, that size of the time quantum is considered to be optimum size. So if we look at this diagram, this also shows the effect of time quantum on the turnaround time. How your turnaround time is going to reduce when your CPU bursts, they become too small or they become too large. So the optimum turnaround time is obtained when your time quantum is at a moderate level, it is neither too large nor it is too small. So therefore this this aspect of round robin has to be very critically analyzed, that is what is the correct time quantum which should be fixed for this. Now this is about round robin algorithm, and we have seen that there is this challenge of fixing the time quantum in this. Now another class of scheduling algorithm is created for processes which can be classified into different groups, right. Like for example, we can have foreground processes and we can have background processes. So this type of scheduling which you are doing after classifying the processes is known as multi-level queue scheduling. So the name itself suggests that this is another type of queue scheduling, but you will have multiple levels in this. And what are those levels? The levels are actually the types of processes that we are looking at. Like one example is given, foreground and background processes. What are foreground processes? Those are interactive processes. Background processes are those processes which are actually batch processes. Now multi-level queue scheduling, in this two types of processes have different response time requirements, because we know that front end processes or foreground processes, they are more time critical, they have to have very short response time, whereas batch processes or background processes, they are they are not so critical in response time and they can be allowed to wait also. So, therefore, the foreground processes will be given a higher priority over the background processes, also because they are interacting. So, we say that foreground processes are externally defined processes, whereas background processes are system's own processes. Now, in multi-level queue scheduling, basically the same queue is partitioned into several separate queues, and the processes, they are permanently assigned to one queue, right, generally based on a particular property. Now, property could be say memory size or priority or the type of process, and each queue will have its own scheduling algorithm. So, what will happen? Separate queues will be used for foreground and background processes. The foreground queue might be scheduled by a round robin algorithm, while the background queue is scheduled using an FCFS algorithm. So, what we are saying is that instead of having one single queue, we will have multiple queues, and each queue will have a specific type of process. And how are we going to determine the type of process? There can be several criteria like memory requirement or process interactivity or the priority, etc. And each queue will work separately, that is, there can be a different algorithm for each queue. Now, in addition, there must be scheduling amongst the queues also, which is implemented using fixed priority preemptive scheduling. So, each queue will have its algorithm, and for all the queues together we will have a fixed priority preemptive algorithm. Now, what we will say is that like foreground queue will always have absolute priority over background queue. So, therefore, in this the process also cannot move between the queues. It is rigid, it is more absolute, it is more inflexible, we can say. So, if you see here in this, you can see there are 5 different types of queues which are there, and they are arranged in the order of priority. So, highest priority and lowest priority. So, processes can they cannot move between one queue and the other queue, and the process in a lower priority, say for example the process in the student processes will only be able to get the CPU when all the top 3 processes have been executed, all the top queues are empty, right. So, the first process queue will have higher priority, then interactive processes, then interactive editing processes, then you will have the batch processes, right. So, system process will be the topmost priority, right. So, like this we can have multiple queues which are executing, but queue number 3 will only get a chance when there is no process waiting in queue number 1 and queue number 2, right. Similarly, if a process in queue number 2 is is executing and a process comes in queue number 1, then the process of queue number 2 will be preempted and the CPU will be given to the process in queue number 1. So, like this is a preemptive fixed order algorithm. Each queue has absolute priority over the other low priority queues, right. So, only when the upper queues are empty, the lower queue can get the chance, and then also that also can be preempted, right. Now, in this case we have another possibility that we use the time slice between the queues, right. In this case every queue will get a certain portion of the CPU time, right, and then it can be displaced. Say for example, the foreground background queue is there. Now, foreground queue can be given 80% of the CPU time for round robin scheduling among its processes, while the background queue receives 20% of the CPU time to give its processes on the FCFS basis. So, like this the multi-level this can work. But the main problem with the multi-level queue scheduling is that the processes are assigned permanently to a queue. The processes cannot move between the queues, and for every process there is a fixed queue. So the process cannot enter other queue. Once it enters one queue, it will have to be there. And it is, processes cannot change their nature also, right? If it is a foreground process, it cannot become a background process. So this entire algorithm is advantageous when we are looking at a low scheduling overhead. That is correct, because there is, there is less context switch time which is required in this, but the overall algorithm appears to be a bit inflexible. So another improvement over this algorithm is the multi-level feedback queue scheduling. Now the name itself suggests that it is a variant of multi-level queue scheduling, but in this the processes can move up and down between the different queues. Now in multi-level feedback queue scheduling, the contrast is that the process will move between the queue. That is, now the idea is to separate the processes according to the characteristics of their CPU burst. So the process will not be fixed into one particular queue. Now if a process uses too much of CPU time, then it will be moved to a low priority queue, right? Therefore what will happen, that the input output bound processes or the interactive processes in which a large amount of time is required for the IO burst, those will be given a higher priority. In addition to this, a process that waits for too long in a low priority queue, it may be moved to a high priority queue. So this is the form of aging that we had discussed, that automatically the priority of the process will go on increasing as long as it is waiting in the ready queue. So this form of aging will also prevent starvation. No process will be waiting for indefinite amount of time. So if we look at this queue, now in this case the queues are based on the CPU slice time. So we have 3 slices here, 3 queues here, one with a quantum of 8, the other with a quantum of 16, and the third which is an FCFS queue. Now in this, if these are the 3 queues, we can number them from 0 to 2, okay, and 0 to 2 means that the scheduler will first execute all processes in queue number 0. When queue number 0 is empty, then it will execute the processes in queue number 1. After queue number 1 and queue number 0 are empty, only then the processes in queue number 2 will be executed. Now if a process which is in queue number 2 is executing and a process arrives in queue number 1, so then what will happen? The process will be preempted. Likewise, if a process in queue number 1 is running and a process arrives in queue number 0, that will be preempted. So therefore in this it is fixed queue, it is multi-level feedback based queue, but it is also preemptive in its implementation. So a process which is entering the ready queue is put in the queue 0. First it is put in the queue 0. Now a process in queue 0 is given a time quantum of 8 milliseconds. Now if it does not finish within the 8 millisecond, then it is moved to the tail of Q1. Q1 means it is the queue of 16 milliseconds. Now if the Q0 is empty, the process at the head of Q1 is given a quantum of 16 milliseconds. Now if it does not complete, then it is preempted and then it is put into the Q2. Now in Q2 we have seen that it is an FCFS queue, but they are only but they only run when queues 0 and 1 are empty. So basically the shortest process will be given the highest priority. So in a way this is an amalgamated, or it's a combined or composite kind of algorithm where we are using the concepts of multiple algorithms. So we are using here the concept of time slice also, we are using here the concept of priority scheduling also. Now this scheduling algorithm, it will give the highest priority to any process which has a CPU burst of 8 milliseconds or less. Such a process will get quickly get the CPU, it will finish its time burst and go to its next IO burst. Now processes which need more than 8 seconds but less than 24 milliseconds will go in the queue number 1. They are lower priority because they are still but they are still more than the processes which require more than 24 milliseconds. So long processes automatically they will go on syncing to queue number 2 and they are served in FCFS order with any CPU cycles left over from queue number 0 and 1. So there will be instances where both queue number 0 and queue number 1 will be vacant. Now in this case different parameters can be used like number of queues, the scheduling algorithm for each queue, the method used to determine when to upgrade a process to higher priority or when to downgrade the process or demote a process to lower priority. Then another very important aspect is the method used to determine which queue a process will enter when that needs to be served. So therefore this feedback based scheduling is configured to match specific system requirements, and it is unfortunately it is not the most complex, it is because it is very complex algorithm. So it is not easily implementable and it requires a lot of other parameters to be defined. So this was about the queuing algorithms, the CPU scheduling algorithms that we have done. We will be continuing with another concept related to the operating system in the following lectures. Till then, please keep watching CEC. Thank you.